Okay, our focus on this video is going to be conservation of mechanical energy. So when we start talking about energy, one of the biggest ones is just the mechanical energy of the system. So this is the sum of the kinetic energy and the potential energy of the system. Now, if we have spring and gravitational, this is all of the potential energies. So when we start talking about conservation of energy, if we are in an isolated system, we can draw a bubble around it, where we have only conservative forces causing energy change, then the kinetic and the potential can change, but their sum cannot change. So that means the energy we start with in the system is equal to the energy we end with in the system. So let's look at this picture here. So here we have a pendulum. So we are going to start pretty much at any point on this pendulum. I'm going to pick a spot where maybe we have pulled it all the way back. So here we start, the velocity is 0, and we let it go. So initially, our potential energy is the only energy in the system. That's gravitational potential energy. As that pendulum swings, that energy starts transferring. At some point, it's a good 50-50 split. At the bottom here, our energy is now all kinetic. Potential is 0. Now, how is that possible? I can declare the bottom of this pendulum swing to be potential 0. I get to declare where 0 is. Now, as it swings up the other side, we start seeing that conversion from kinetic back to potential. And when it stops here on the other side of that swing, we are now back to all potential energy. As it swings back, we have that blend. At the bottom of the path, it is again all kinetic, and it just keeps repeating. If we have no external forces acting on it, completely isolated system, this pendulum could keep swinging forever. But this is that conservation of energy, that the energy total is going to be the same. It just may be in a different form. So let's look at a problem where this works. So here we have a runaway truck with failed brakes going downhill at 130 kilometers per hour. Now, if I convert that to meters per second, we're looking at 36.1 meters per second. Now, this is just before, so right here, a driver steers the truck up a frictionless, that's keyword here, emergency escape ramp. Now, if you've been to Colorado, you have seen the runaway ramps that go up the side of the mountain trying to slow a truck down if it burns up the brakes. So that escape ramp has an inclination of 15 degrees. So this is going to be 15 degrees. We have the truck's mass. The mass of the truck is 1.2 times 10 to the 4th kilograms. And we want to know, what is the minimum length the ramp must have to stop the truck, at least momentarily. Now, it will eventually come back down some. But what is the length it has to have to stop the truck? And will that length increase, decrease, or stay the same if we change the mass or if we change the speed? So let's get started. So we need to know initially, what are we starting with? So if we are saying there's no frictional force acting, that means the initial energy we start with is going to equal the final energy at the top of that ramp. So initially, at the bottom of this ramp right here, when we start to steer up it, all of our energy is in kinetic. So we have kinetic plus potential, and we have kinetic plus potential final. So initially, this potential energy is 0. So all of our energy is going to be just 1/2 the mass of the truck, that initial velocity of the truck squared. Well, at the top of the ramp, at the length L, we're momentarily at rest, so that kinetic final is going to be 0. So our potential energy is going to be mgh. Now we have to be careful because nowhere in here do we have how h is connected to L. So let's keep this little dashed line going out here. We're talking about this h. So how am I going to find h? Well, that is a question. So let's start by solving for this and seeing if we can translate that into what L looks like. So here I'm going to realize that, what could I just do with that mass? So that should red light us for something right here. What happens if we change the mass of the truck? So notice I just canceled it out. So that means that the height that the ramp has to go is going to be 1/2 the initial velocity squared over g, because I divide by this g right here. So if I put my numbers in, I'm going to have 36.1 squared over 2 times 9.8. So that's going to give me 66.5 meters. But that's not L. That's just the height. So how am I going to find L? Well, I have a triangle. I know the height. I know my angle. So I could say, okay, well, sine of theta is going to be h over L. So that means L is going to be the height divided by sine of the angle. So I could put in that this is 66.5 meters. I've got sine of 15 degrees. So that's going to give me 257 meters. That's 2.5 football fields in length. Bigger than 2.5 football fields. So it has to be about 260 meters long if we're going to be able to ignore friction. So what happens now if we decrease the truck mass? There is no change. We canceled it out. Does not depend on the mass. It depends only on the speed. So what happens if I decrease the speed? So if I decrease the speed, so v is smaller, that is going to be a direct indication that h, our height, is going to be smaller. How do I know? Right here, my velocity squared in the numerator. So if h is smaller, that means L can be smaller too. So if we just decrease the speed a touch, we can make that ramp shorter. All right, so let's look at another example here. So we have a marble being fired vertically upward using a spring gun. The spring has to be compressed 8 centimeters if the marble is going to be able to reach a target 20 meters above the marble's position on that compressed spring. And we want to know what is the change of the gravitational potential energy of the system. So here we go. So the first thing I do is I kind of sketch out what's happening. So I have a spring. It's going to compress down 8 centimeters. Our target is 20 meters above that. So I'm going to declare that to be where gravitational potential energy is 0. Where the spring is smushed, that's our 0 for the target height. I'm going to just declare that to be potential ground is 0. So what we want to know is what is the change in the potential energy due to gravity, due to the gravitational force of the marble Earth system during that 20-meter ascent? Well, at the top of the path, the potential energy due to the gravitational force is going to be mgh. The marble is 5 grams, so that's going to be 0.005 kilograms. G is 9.8, and our height is 20 meters. So that's all going to work out and give us 0.98 joules. So that is our final height. Changes final minus initial. So final minus 0, that's going to give us 0.98 joules for our change in gravitational potential energy. So we then want to know, that was part A, we then want to know what is the change in the elastic potential energy during the launch of the marble. So initially, the spring elastic potential energy is going to be 1/2 kx squared. When that spring launches, the final potential energy, it's going to be 0. Well, there's a problem here. I don't know what the spring constant is. So let's come back to this in a second. What's another way I could look at this? Well, there's no non-conservative forces. So that tells me that the kinetic initial plus the potential due to gravity initial, the potential for the spring force initial, should equal all of the finals. We have energy is conserved. The initial energy should equal the final energy. So I know at the bottom we're at rest when we start the launch, at the top we're at rest when we hit the target. So we're going to go from here. Gravitational at the bottom, 0. When we're up at the target, this is 0. So what that tells me is that the potential energy we start with is going to equal the potential due to gravity that we end with. Another thing we could do is we could rearrange these. So let's go back here for a second. Bear with me. So if I stop right here on my rewind, I could put all of my spring stuff on one side, all of my gravitational stuff on the other. So if I subtract USI and I subtract UGF on both sides, what I get is UGI minus UGF. So potential energy, that is negative change in the gravitational potential energy. Why is it negative? Because it's supposed to be final minus initial. This is going to equal my potential spring final minus potential spring initial. So that tells me that my change in the potential of the spring is going to be negative 0.98 joules. So how, pray tell, can I find my spring constant? Well, it all goes back to this. So final minus initial is going to equal that negative 0.98 joules. So this is going to be B. I'm going to reclaim this as C. So I'm going to have the negatives are going to cancel. 1/2 kx squared is going to equal 0.98. So I'm going to multiply by 2. So 2 times 0.98. I'm going to divide by x squared. So k is going to be 0.98 divided by, I need my distance in meters, so that's going to be 0.08 meters squared. And when I work all of that out, I'm going to get about 310 newtons per meter as my spring constant. So that's how we can use conservation of energy to find that spring constant.